Hi everyone, welcome back. I'm Dagan Brock for Apple2.gs. This is our follow-up video to the first video on Introduction to Programming the Apple IIgs, which was video 0, so I guess that makes this video 0.5, I'm not sure. I have a couple of quick announcements and then we'll get into the computing again. The first thing is I shared the first video online, obviously, and I shared it and kind of tweeted and stuff to Western Design Center, who I spoke about creating the 65816. And they were kind enough to retweet it and put it on their Facebook page, which was a huge thrill for me. But I also wanted to point out that they are still active, they are still putting out product, and they are working on new products, and they have a bunch of great resources on their website. So you should probably also follow them. They are on Twitter at WDC65XX, and on Facebook they have a page, facebook.com/Western Design Center. And I couldn't find the link for today, but we talked about reference materials. They had this available on their site as a PDF. It's still available in other places online. I'm going to try and find the link for this and put it in the video, but I won't cover specifically every little detail of the 65816 assembly language instruction set. I am more concerned with trying to get the message out about programming the Apple IIgs hardware using 65816 assembly language. I'll give you a little guidance along the way, but I don't think you want me teaching you assembly. I'm not that good at it. But this is a great reference if you want to have the full list of all the opcodes, a lot about the CPU and how the instruction set works. It's called Programming the 65816, including the 6502, 65C02, and 65802. Yes, that's the actual title. It's by David IIgs and Ron Lichty. It's a great reference. I actually printed out a hard copy, not just because I like books, but it's actually it's a good one to be able to leave open on things like their instruction set page. Just be aware that, like any good software that is complex, there are bugs, so there are some things that I've annotated on here, which is another nice thing about printing it out. I can fix that. But hey, we all make mistakes, right? And of course, I have to thank all of you who watched the first video and tried some of those things out. That was my goal. I really appreciate it, and I really appreciate all the feedback. So I think this is kind of the format I'll do, where I try and present to you a produced video that gives you a bite-sized chunk of one piece of the Apple IIgs, so that you can take that and get some real comprehension on a small piece, and we'll build that up over time. And then I'll do a follow-up video where I take your feedback and try and clear up any confusion, clear up any errors. There were some things I misstated in the first video, and that's going to continue to happen. But as the series progresses, or at least the parts that I'm creating, there will be less video of me in front of a camera, I promise, and honestly there will probably be less use of real hardware. The reason for that really is just that I think it makes sense to do it as a screencast using an emulator window. It'll be easier for you to see, and it actually makes it a little easier for me to shoot and edit that. But you know, coincidentally, what we did in that first video does not always work very well on an emulator. So a lot of things regarding specific video hardware or sound hardware can have difficulties in being emulated 100% accurately. And in fact, some people did try it on an emulator, some of the border effects that we did in the first video, and said it didn't look right. And that's not surprising at all. Finally, I am playing a little fast and loose with terms. Part of that is I don't want you to get bogged down in details that maybe aren't relevant to what I'm trying to communicate to you. But of course you're welcome to ask me about it, or correct me. I may have actually just made a mistake when I say some of these things. But one example would be that I typically use the terms 65816 and 65C816 or W65C816 interchangeably. For our intents and purposes, we're talking about the same instruction set, but I don't want you to be confused and say, hey, I thought he said it was that other processor. Is it this processor? It's conceptually all the same. So things like that, I may, like I said, kind of gloss over it a little bit just because it's not important for my immediate message. Alright, enough of me talking with no computing. Let's get back to the computer and talk about what happened the first week and where we go from there. Okay, in the first week we were talking about the border colors and text colors, and I said that there were 16 possible color values from 0 to F, so that is correct. But I accidentally said that this corresponded with the high-res colors on the Apple II. Of course, that is incorrect. I meant the low-res colors. High-res mode on the Apple II has 6 colors, basically. But the low res, the big blocky chunky mode, has 16 colors. Okay, I'm just going to jump over to basic real quickly and demonstrate an easy way to see the low res colors that are available. You can type GR to go into the low res graphics mode on an Apple II, text to go back to the text mode here in basic. I'm just going to type this as a one-liner, so I could spread this out across multiple lines, but I'll use a colon in between my basic statements. We'll do a loop just from 0 to 15, so that's 16 colors starting with 0, which we already talked about that being black. And we'll set the color to the current iteration of the loop there, and then we'll just plot it at its relative locations. So color 1 will go at 1, 1, and so on, and loop through to the end. So you can see there we have our black up in the top left, and red, which is 1, dark blue is 2, purple or violet 3, so on up to F. I'll just do one more just for fun to make it a little easier to see the actual values. I'm just going to take a string that represents our 16 possible hex values. Same thing, we'll turn our graphics screen on. I'll go to the next line so you can read this a little easier. Like before, we loop through. If I could, almost made a big typo there. And set our color like we did before. This time we'll plot all the pixels at the bottom of the screen. And then we'll just print a portion of our string that I defined up there. Of course, strings are indexed differently here. We're going to start with 1 and count up, so that's why I add 1. And we don't want a new line, so the semicolon basically means concatenate. So it's going to suppress new line printing on the end of that. And like before, we're just doing one loop, so we'll let it loop through to the end there, and this will shift our lines up a little. Okay, so same thing as before. Now you can see it a little more easily, 0, 1, all the way up to F. Let's look at one other thing that's kind of useful on the 2GS, and I don't believe this is in earlier versions of the firmware. So we talked about CO22, CO34, CO2E, but we can't use those values if we wanted to play with them from BASIC, if you ever want to do that. Let's go back into the monitor, and you can type in a hexadecimal number and type the equals sign and get the decimal value back out. So that's one way to find the address location of programs that maybe you've put in the mini assembler, and then you can call them from assembly. So for instance, we've also been doing this call -151. We can convert from decimal back to hexadecimal. This looks a little confusing because it's a 32-bit value, but basically they're saying -151 is equivalent to the address at FF69 if you just take the last 4 numbers there. Another one we'll do is, you'll see a lot of programs that have call 768. So now you can see that is actually value 300, which we were using for our scratch space for writing our programs in the first lesson. So again, oops. 49204. Hit Control C to go back. So if we do 49204 0, we just set our border color black. So that's really all. I could write a little program, you know, and loop through in a for loop and set these border colors kind of like we did last week. That's a bit slow, obviously, and really I just wanted to show you the low-res colors and how we could do some quick prototyping in BASIC, and now you also know if you want to play around with the mini assembler how to mix that into your BASIC. You know, you could do something at 300 and then call it at 768. So now let's get into some questions from last week. Okay, so there were a couple of questions on the monitor last week and the mini assembler, and I want to address those first. The first thing was, when I was listing address locations last time, somebody pointed out that they understood that these are the values at the location. So location 0 has the value 4C, location 1 has the value 3C, and they didn't understand what these other marks were to the side. So that really is just your basic ASCII representation of what is in that memory space. A lot of times it's not very relevant. And as you can see, when we just hit enter to continue to list out the memory locations, same thing here. You have a dash in between the values and their ASCII representations, and a lot of them show up as periods. So these zeros show up as periods, which doesn't mean that that is how the character display would show them. So if I put a 0 on the screen, it actually shows up as an inverse @ symbol. So that's all those are. This is basically showing you what potentially it looks like as text. Sometimes you can recognize some patterns in there when you're looking through things. And the 2GS actually has a really nice ability to enter strings, I believe. So I should be able to put in a string like this, and of course if I list that as assembly, it's not going to make any sense. But if we were to do that 300, you can see my string over here. It lists a little weird. Let's list it out. 300 to, let's say, 320. So you can see test string here. It wraps around, of course, and then of course you can see the text values over there. I'm not sure. I believe you can do both high or low bit entry. Let's try. We'll just do the first word. So that it didn't like the single quote version. I believe maybe it's only high bit set. Yeah, that's basically all this is showing, is that there's an ASCII representation. The other question that came up was on the Apple IIe. We're looking at an Apple IIgs emulator right now. He said it didn't have this 00 / in front of it, and that is true. So what is that? Well, we can actually change that. You know, we can go from 0 to 1, and this actually looks different than bank 0. If we go back to bank 0 and look in there, there's values on this 0 page here. There's a bunch of zeros on 0 page here. So what I'm actually doing is switching memory banks. And that is how the 65C816 addresses more than 64K of memory. It uses a bank address. If you actually look at the chip, you can see where the bank address lines are. So in the mini assembler, it just shows you what bank you're currently in, and typically I've just been doing all of this stuff in bank 0. And that's important because bank 0 is essentially the same bank that you get on an Apple IIe or an Apple II Plus that has 64K. You know, and the ROMs and everything, they're always in bank 0, just like any other Apple II. When we start doing more advanced software, stuff that launches from GSOS, it will load up into any bank that it can find available, and it does that using things like the memory manager, which we'll get into. So for now, you don't really need to worry too much about the banks, but this is how you switch between the different 64K slices of memory. And we'll go into more detail about this, but like I said, bank 0 is like your other Apple IIs. Bank 1, E0, and E1 are kind of some special banks that have significance that we'll get into as we go through this lesson, or not today's, but in future lessons. So hopefully that answers those questions. There was one other question where I believe I had done, you know, one of the
the programs to loop indefinitely, and I did something like this. So it basically would increment the border color and then branch back up. So somebody asked about this. Why do a branch instead of a jump? Branches use relative addresses. So you can see right here, it's going to go back 5 bytes from where the program counter is. And that is actually faster than loading in a whole 16-bit address or a 24-bit address in the case of a long jump. So branches are typically faster, and they're not available on the 6502. They're available on the 65C02 and of course the 65C816. So typically I'll use branches for tight loops like this instead of a jump. They have different uses depending on other necessities too, like if you need to use a jump table or if your address is more than basically 127. I believe the branch range is -128 to +127 bytes away from the program counter location. So it's not a huge range, but if you can take advantage of that, you shave off 1 byte of code and I believe 1 cycle. Of course, the branch is always taken, so you don't get any cycle shaved off from when it's not taken like you would with a normal conditional branch instruction. So hopefully that answers that sort of question. For those of you coming from 6502, there are definitely instructions that are in the 65C02 and 65C816 that I won't be covering in this kind of detail, but if you're curious about them, go ahead and look them up in the programming manual for the 65C816 that we talked about earlier. So last week we did this little demo where we read one of the video registers and synchronize that to the border color. And in the video I showed you this screen, close-up of my screen, and I've very intentionally did a close-up on the left-hand side. Somebody actually noticed that there's some artifacting on the right-hand side, so I'll go ahead and show you that real quick. So this is actually slowed down so you can see it a little better, but there's a little flicker there happening on the very tail ends of these lines. So to really explain this, we first have to take a step back and talk about Crt displays, the old cathode ray tube displays that some of us grew up with. And those use a fluorescent screen, and they've got these little clusters of the primary colors, red, green, and blue, the primary colors of light, in clusters of normally 3 called triads. And we get different colors by firing an electron gun at them and exciting those little phosphors. Okay, I think the best way to explain this is using animation, and it would take me a long time to do a nice clean animation, so I'm just going to try and draw this out real quickly, and hopefully you'll get the gist of it. But if you've ever looked inside one of those old CRT picture tubes, you would have seen a big piece of glass on the screen that sort of tapers back to this electron gun in the back. And what the electron gun does, like I said, it fires out electrons that excite the phosphors. But to get them in position on the screen, it uses some magnets normally coiled around the neck area there. So those electrons will fire out and get bent by the magnets to reach their intended position on the screen, kind of like so. And basically it keeps bending it, and what it's doing is it's going to, basically start here and excite these phosphors in what we would call the top left pixel, and slowly move across the screen, in relative terms, to scan all of these phosphors and excite them and draw that first line. So what happens when it gets over here? It needs to somehow go down and do the next line, and it does that, but it goes into what we call a horizontal retrace mode. So it's not actually drawing, it's basically, for all intents and purposes, turning off the gun here and getting it back into position, scanning down here, sort of diagonally, like so. And then it would just, from that point, go ahead and do the next line, and the next line in the same way. Oops. Right, so you do kind of get a zigzag pattern like that, where sorry, the zag here is not drawn. Okay, that's all well and good. So what happens when it gets down to the bottom of the screen is something quite similar. After it's done drawing this last pixel down here, it's doing this line, happy gun scanning along, hits the bottom of the screen. It needs to start over and do the whole thing again so that we get essentially 60 updates per second. So it goes into a vertical retrace mode, much like the horizontal one, but this time it's scanning up. And it's actually doing both. It's doing the horizontal and vertical reset at once. So it's pulling back to the left and pulling up to the top. So it basically goes from down here up to here and starts that whole process again. And one other note is that on old TVs, they would actually do this thing called overscan. And in overscan mode, they would basically show you all of this out to the edges of the screen. On computers, they will typically do something called underscan, because you don't want to lose any information because it's hidden behind the plastic bezel on the front of your screen. So on a lot of computers, they'll do underscan, and that's why we would have something like a colored border here on the 2GS. Okay, so hopefully that kind of explains the raster and what's happening when it's scanning across the screen. But that still doesn't explain our little anomaly. Let's go back and run our little program again, where we load the vertical counter in CO2e and store that as our border color in C034, and then do that infinitely. And of course I'm running it in an emulator. This one happens to still show a little bit of the anomaly, enough for our experimentation here. However, it's not as accurate as the real hardware, and there's also some artifacting over here which would not exist on real hardware. So this is kind of the problem with using emulators, but it shows enough of our condition here that we can talk about it. So if you'll notice, when I did the first demo, I said these essentially correspond sort of to the line number divided by 2. So we have 2 lines of color 0, 2 lines of color 1. So you look above this color 0, it's actually turning black up here before. So why is that? I believe it just has to do with the way the video registers assume their line. Remember we talked about underscan? So this is the information that we are interested in, this very top line, and then the next line and the next line. All of the border part is not interesting. This is just underscan. So I believe that the video register, once it hits the end of this line, it says, hey, I'm done with line 0, really. I'm going to go on to line 1. And then when it gets to line 1, it says, I'm done with line 1 right here, so really I'm on line 2. And we're polling it fast enough to catch it just in time before it even goes into the horizontal retrace mode. So I'm not 100% sure on that, but I believe that is why. So when it gets over here, and we are detecting this, what could we do to fix that? Well, there's that horizontal retrace period that takes a little while to push the electron gun all the way back over to this side and start. So you can introduce a little delay so that when it goes off this right-hand side, you won't see it anymore, and that should really fix it for us. There's other ways to do timings, like we've talked about with interrupts, but let's go ahead and experiment with this a little bit. First, we need to revisit part of our lesson from last week where we talked about C02E, the vertical counter, and I basically said that it represented the current scan line divided by 1. That's mostly true, but that's not exactly how it works. And if you look at the appendix in the Apple IIgs firmware reference, it doesn't give us much more information than that. It just says there's C02E, and that holds the address for video control bits V5 through VB, and then there's a related counter, C02F, the horizontal counter, which has the addresses for read of video control bits VA through H0. That is technically correct, but an absolutely useless bit of information without context. So very frustrating there that it's not in the really well documented at all in the firmware reference. However, later on Apple did tell us a bit more about what that did in their tech notes. You can find the tech notes on the internet in many locations, including apple2.gs, and we're looking for tech note 39, which deals with the Mega2 video registers. So this really discusses what those counter bits mean. So what we now know is that there are two registers we're concerned with if we want to get the actual screen position, the vertical counter and the horizontal counter. And normally we think of bytes as having bits from 7 to 0, but these two have special names for all of the bits based on what their function is. And if we read that tech note closely, it actually tells us that the vertical counter is actually 9 bits and the horizontal counter is 7 bits. So what's happening is the horizontal counter is actually holding one of the bits because it won't fit into the vertical counter. So we need to basically put those two together somehow in order to tell where we're really at on the screen. Let's experiment with this. We'll do another version of our first program where we took the vertical counter register and stored it as our border color. But this time we'll start with the horizontal counter register at C02F, because remember we need that high bit, which is actually the least significant bit of our 9-bit vertical counter. So to get that, we'll load the value and then shift it off into our carry flag so it'll be stored for later. We'll throw that value away though and load our actual vertical counter register, and we'll rotate left this time to basically shift that carry into the least significant bit. And what that gives us is the actual value we want for the line number on the screen. We may have chopped off some of the higher values, but we're not concerned with those. We just need 0 through 199. The Mega2 video hardware may use some of those higher values as it's doing the top and bottom border, but you can read the tech note to get sort of the details on this. So we'll take this final value that we have and store that as our border color and branch back like we did in our initial example. Great, so I don't know if you can really tell from this screen, but now we're getting it on every line, and it doesn't seem like in the emulator we're getting any fuzzing here on this right hand side, and that could just be due to the fact that we're taking a little longer to get our result because we're actually taking a value, shifting it left, merging that into this secondary value. So you know, that could be helping us here. Okay, so we'll make a routine that we can call that we'll just stick at 350 for now with the line number that we want to wait for in the accumulator, and I'll just kind of store that off somewhere, being a little sloppy here, but then we'll do the same thing as before. We load our C02F and shift that left, load C02E, rotate left. Now we have our value for the line number on the screen. We'll compare it to the value that we stored at 370, and if it's not equal, we'll branch back to not the beginning of this routine, but the second instruction, the load A C02F, and until we get the value we're looking for, then we'll return. Now I'm going to write a second program starting at 300. I'm just breaking out to give it a little visual space there. So let's try this. Let's load the number 20 hexadecimal 20, so that's actually what, 32, something like that, and try to use our subroutine at 350. And when we get to that line, we will store 0 in the border color register. That should turn it black, right? And then we'll do a second call to our routine. This time we'll do 30 and call our routine. And when we get back this time, let's load a different color. Believe that is the regular blue background color. And we'll just branch back up and do this indefinitely. Branch back to 300. So if all goes well, great. We've achieved sync here. We wait for line 20, and then we set the border color to black. And then we wait for line 30, hexadecimal again. So this should be 16 lines right here. It looks about right. 2 lines of text. And we set it back to the original color. So now we've basically made a much better routine for that, and we can animate that. We can also do some other things to optimize that routine when running in 16-bit mode. But I've spent a lot of time kind of researching these registers and putting this material together to try and explain it. So I'm going to stop there for today. That's all I'm going to do for the follow-up. Hopefully that clarified some of these things for you, and I do apologize that it may not have been as interesting as the first video, but this is kind of the format I'm going for, where I'm going to do a little bit more focused on the introduction to new material and just kind of blast that out there, and then I'll wait for feedback and try and comment on all of that to give the details to the people who are really interested and have the time and motivation to listen to me ramble on about this stuff. So thanks for watching. We'll be done with border registers for this week, and probably for good. But some of these things involving the vertical retrace and horizontal retrace are going to come up again when we start talking about animation. Hey, you stuck around. Secret bonus part. So let's make a little demo now. Remember from earlier we knew that 300 was 768 in decimal. Let's see if this works. There you go, my friends. Now we have some border effects and some text effects going on. I didn't go all the way up to the top or the bottom there, but pretty close. And this does not work very well at all on emulators, so I'm sorry if you're not using real hardware. You may have something completely different, but it looks pretty good on the real thing. And part of the reason I may not be able to see it on there, but it is using
a dark blue, and then the medium blue, and then a light blue, so you can use this to sort of make those copper bars that you would have seen in demos of days past. And there's a couple of different built-in colors that you can use for that, and you can mix and match obviously out of the 16, but it's just a little fun, and that's all. I am seriously done with border colors, and I hope you had fun. Bye.